Imagine getting a simple cut, something that's probably happened to you before countless times. These openings can be sites where harmful bacteria can infect and wreak havoc in your body. But it's all good, right? In case of infection, we have effective treatments for it in the form of antibiotics. But what if I told you that possibly one day in the near future, these antibiotics won't work? That the bacterial infection from that small cut could be a death sentence? While extreme, we are currently getting closer to this reality of a post-antibiotic world, but the OneRing Oxford team is trying to solve it. The problem that the OneRing Oxford team is trying to solve is the global issue of antimicrobial resistance, aka AMR. AMR occurs when antibiotics are no longer effective in eliminating a bacterial infection due to the population of bacteria becoming immune to that antibiotic. This immunity arises from random mutations in normal bacteria that enable antibiotic resistance. When antibiotics are used, only the bacteria with the mutations enabling resistance survive. Then, those resistant bacteria multiply, creating a population of only antibiotic resistant bacteria, which you can see in the diagram in the middle of the slide. People who are impacted by harmful bacteria that are resistant are unable to be treated by antibiotics, leading to potentially fatal impacts. According to the World Health Organization, the forecast is that by 2025, AMR could cause 10 million deaths annually, which is more than cancer and diabetes. The iGEM team's model predicts a 3.29% annual increase in AMR deaths. Bacteria can also undermine the effectiveness of surgical procedures and cancer chemotherapy, which use antibiotics to keep infections at bay. In the livestock industry, antibiotics are used to reduce losses from bacterial disease outbreaks among animals. AMR presents a risk to this industry, as uncontrollable bacterial disease outbreaks could have significant impacts on food supply. What has been done to try to solve this problem? The main current solution to the increasing population of antibiotic-resistant bacteria has been to discover new antibiotics. However, in recent years, the rate at which new antibiotics are being discovered has diminished. Other solutions including antimicrobial peptides, aka AMPs, that inhibit bacteria and bacteriophage delivery systems that can selectively infect bacteria, however, have been proven to be rather costly and difficult to scale up. This iGEM team has engineered a plasmid called OneRing that, when inserted into the pathogenic AMR bacteria, can eliminate it. There are two main systems that the Oxford iGEM team have carefully designed: the delivery system, which is how the OneRing plasmid gets into the targeted resistant bacteria, and the killing system, how that bacteria is eliminated by the OneRing plasmid. Both systems are inspired by natural mechanisms in which bacteria function, which we will also explain further. Before we dive into these systems, however, let's look more closely at the OneRing plasmid itself. One of the main features of the plasmid is the Cas12a gene, which expresses the CRISPR-Cas12a that will be used to cut the DNA of the targeted bacteria, which we will also explain further. And there's this strong P ultra promoter that allows for high levels of gene expression of this gene. There is also a synthetic target array in the plasmid, which contains genetic information for the guide RNA that will assist in the killing system to direct CRISPR-Cas12a to the target DNA that is intended to be cut out. Additionally, the origins of replication also ensure a high copy number and significant replication for both gram-positive and gram-negative bacteria, which you can see over here and over here. Finally, there is the RP4 origin of transfer, which is part of the conjugation system, which is what enables the plasmid to be delivered from the donor bacteria, where the plasmid is first inserted, to the targeted resistant bacteria. The rest of the plasmid is made up of this backbone. Now we will go into more detail into the systems that make up the OneRing solution.
So first up, let's figure out how the plasmid gets into a target bacteria that we want to kill. So the delivery of the OneRing plasmid is done through bacterial conjugation, which is a gene transfer mechanism that happens naturally in bacteria. So in this diagram here, the bacteria on the left in blue represents the donor bacteria, and the OneRing plasmid is inserted into this donor bacteria. And one feature that the donor bacteria needs to have is a F factor, and this specific feature allows bacteria to transfer genes to other bacteria. This F factor is needed because it allows the pili of the donor bacteria to be stretched and become a path that connects the donor bacteria to the recipient bacteria, and that is the path that the OneRing plasmid will be transferred by. And the specific conjugation system used in this case is called the RP4 system, and a unique feature of the system is that it is agonistic, and this means that it does not require surface membrane protein for membrane penetration. This ensures the suitability for the OneRing plasmid for both gram-positive and gram-negative bacteria. In the end, our goal is to kill the AMR bacteria. So how exactly does the OneRing plasmid achieve that? That's when we will move on to the killing system. This plasmid that I've circled here is the OneRing plasmid that we are using. And in this section, I will focus on how the different parts of the plasmid work together to achieve the goal of killing the bacteria. So looking at this diagram on the right, we will look at our first unique feature of this plasmid is that multiple different arrays can be inserted into the same plasmid as the protein. So by inserting one plasmid, it means that a wide variety of pathogens can be eliminated through just this one protein because of the different arrays that it can express. Another feature of this is that the array can be edited very easily through synthetic biology. And how it works is that the protein binds with the RNA and they would travel to the corresponding sites in the recipient bacterial DNA. The protein will work and cut through the DNA, and this will cause the cell to die. So now that we know about the mechanics behind killing AMR bacteria, how can the OneRing plasmid be actually employed in real life to actually solve the issue? Well, because the issue affects the human population and animal population in separate ways, the solutions will also be different. So specifically for companion animals and livestock, the OneRing system can be employed through food supplements, just like probiotics that are taken regularly in their diet. Once they're in effect, the supply of animal products like meat and dairy wouldn't be influenced. More specifically for the companion animals, once they are healthy, them around humans will also prevent many zoonotic diseases from spreading. And for humans, the plasmid is best suited for treating skin and wound infections according to its design and its high specificity in targeting pathogenic bacteria. So hence, it would be a great inclusion to have in wound treating lotions or gels. And just to sum things up, the problem that this team addressed is the rise of AMR and its impact on healthcare. More specifically, refers to the emerging bacterial infections that we don't have solutions to that are coming up in the very near future. And also the livestock industry, which refers to possible dramatic drop in supply of meat and dairy products. So the solution that the team came up with is, of course, the OneRing plasmid, and key components like the Cas12a gene and the synthetic array work together in the killing system, and the RP4 region of transfer is a key component in the delivery system. And impacts of the solution includes stable livestock industry and a great foundation for treatment of emerging internal bacterial infections in the future. And thank you.